All right, hello everybody. I'm actually very happy that I have a chance and invitation to present you some of my work, which is directly related to hydrogen economy as uh, one of the key focus um, areas of the Energy Transition Institute. Thank you for the invitation, and with that, I'm going to basically just start introducing myself for a few slides and then go with material. So basically, I joined University of Houston in 2005 after spending 4 years in industrial research and 2 years at Brookhaven National Lab. I was also doing my PhD at Arizona State University. So generally, my group is working in the area of material science, but for this particular occasion, I will be addressing only the topics which are related to hydrogen economy, whether we use our knowledge and experience and scientific efforts to improve the materials or develop new concepts. You're going to be hearing about this. Now, just to introduce myself a little bit better so you can understand what the group is doing, we are specialists in different types of chemical or electrochemical coatings, which could be applied to different surfaces and for different applications, standing from corrosion, tribology, catalysis, etc. So just to give you an example here, our recent work demonstrated for the first time chromium coatings which are crack-free from chromium-6 electrolytes. Then we also focus on magnetic materials for microelectronics application, where we develop very different types of films for magnetic induction, recording, etc. And finally, the thing that is going to be presented a little bit more in this occasion is the work we are doing, which is directly supported by Department of Energy and Energy Transition Institute and Shell, related to synthesis and application of hydrogen permeation barriers made of copper. Then my group also developed very different synthetic methods for catalyst monolayer synthesis, which gives certain advantages for fuel cell application, electrolysis, and so on. We also use those special methods, such electrolysis ALD or electrochemical ALD, to modify nanoparticles as a catalyst material for different applications or to apply certain gas permeation membranes, which is related to hydrogen separation, fuel cell catalyst design. But what I'm going to discuss a little bit more here in a particular case is the hydrogen isotope separation as a direct side consequence of electrolysis, which we consider today as one of the sources of the ultra clean hydrogen, where I'm trying to convey the message that most of the money actually producing hydrogen will be actually available if we at the same time do hydrogen isotope separation. Therefore, this would be very profitable endeavor. Besides producing hydrogen, we could make money producing isotopes or separating hydrogen isotopes. Finally, in the area of sensors, I do a lot of work in chemical sensing for gas and oil industry. For this particular case, I will be addressing the sensors which are related to hydrogen or sensing concept, but it will be demonstrated using the data for the chemical sensing of anions. We do a lot of work on magnetic field sensors, ultrasound sensors for different applications in military or medical areas, and so on. So with that, I'm going to start with the first third of the presentation, which is palladium monolayer catalyst. And those are atomic monolayers, new paradigm in electrolytic hydrogen isotope separation. This is a work recently accomplished and funded by National Science Foundation, and its roots have in generally several facts, where the electrolyzers are becoming very popular these days because cheap electricity as a source of energy could be actually used effectively to produce or to purify hydrogen. And therefore, electrolytic processes where electrolytic process meaning, electrolysis of the water is considered also one of the most efficient process to separate hydrogen isotopes, whether it's a tritium from light hydrogen, deuterium from light hydrogen. It doesn't really matter. The separation factors during electrolytic processes are the highest ever recorded. The relevance of that could be also for upcoming fusion reaction or fusion reactors, which next year will be demonstrated for the first time on a large scale. The ETI reactor in France supposed to be online next year. Therefore, the significance of hydrogen isotopes will grow with the time. Pure D2O or pure heavy water or tritiated water are extremely expensive. For example, I can give you an idea. The 100 grams ultra pure D2O or deuterium oxide, if you want to call heavy water this way, is a water between $600 to $1,100 depending on the market. And this is the commodity that is strictly controlled by the governments, which means you cannot buy as much as you want on the market. It has to be approved because it's a strategic material used in the breeding reactors to produce enriched uranium or plutonium, etc. So it's actually very profitable, material to produce. And as I say, since we already consider electrolyzers for production of the hydrogen, therefore, as a side product, which probably would cost more than the produced hydrogen, would be ultra pure or heavy water, or eventually deuterium. So the concept that we propose or actually demonstrate here is based on a monolayer catalyst, which is having a epitaxial relation with the substrate. Therefore, if the substrate has a bigger lattice than the palladium as an active catalyst for hydrogen water electrolysis, then the d band or electron density on the surface is shifted upward, meaning more energy in electron d band is available for overlap, and therefore the catalyst is more reactive. If the strain, because of the epitaxial relation, is negative or compressive, then activity of the catalyst is compressed. So therefore, if you put palladium monolayer on gold, you expect that palladium monolayer should behave better or act more actively than the bulk palladium, which already is very active for electrolysis. If you put palladium monolayer on ruthenium, you should actually suppress this activity. And this is first demonstrated studying some absorption of hydrogen, electrochemical absorption of hydrogen on this palladium-covered different substrates. So therefore, we already have a prelude that points the correct catalyst choice. Going further, I just want to give you an idea that one of the rate-limiting steps during the hydrogen evolution reaction is the hydrogen recombination on the surface. Therefore, at lower potentials, which is typically the case when you use very active noble metals as a catalyst, the hydrogen recombination is the rate-limiting step, and this step dictates that the separation factors between hydrogen isotopes, in this particular case, I'm giving an example between light hydrogen and deuterium, is given by this expression where you can see that in exponent you have the Planck constant multiplies the frequency of the vibrational bond of hydrogen and deuterium, actually difference between them. Therefore, if you do anything to the catalyst to enhance the strength of this bond or enhance the frequency, the separation factors will go up. And so if the palladium is extra active, which means it will bind hydrogen stronger, separation factor should be actually higher. So in conventional electrolyzers, which are used for hydrogen isotope separation, iron and nickel are well known, and they require relatively modest overpotentials, and they're relatively cheap comparing to the noble metals. Their hydrogen separation factors are order of 7 to 8. Then we have a hyper D alloys, which have a slightly lower separation factors, but they also are more durable and they can withstand longer operation times. And here we fall into the palladium platinum, which are extremely expensive, but they have they require very lower potentials, which means a low energy intensity for operation. And therefore, their cost is maybe high when you think about per gram, but actually their efficiency is very good. So you're not spending too much electricity on electrolysis. And therefore, with our concept, we can actually go around this price per gram and use only a monolayer catalyst, whether it's platinum and palladium. Here we talk about palladium, and therefore the cost of this precious metal could be significantly reduced. So how we create these palladium monolayers? We use gold, or just to give you an idea here, the palladium forms perfect adsorption monolayer on gold through the process called UPD, or under potential deposition. You can see here ultra pure clean gold surface through the process of electrochemical deposition is actually decorated with exactly a monolayer of palladium, which corresponds to this peak here where the palladium deposition actually is accomplished. So therefore, we don't have to really do too much to create this ideal catalyst for a hydrogen isotope separation. In the case of ruthenium, where we want to demonstrate the opposite effect of the compressive stress, the lucky thing is also that palladium grows 2D on ruthenium, and basically what we really need to do is control the charge at pass, which corresponds to about a monolayer of palladium, and then stop the process, and that's exactly what we do. And so the first thing that I want to prove you is that the theory behind the separation factor definition is correct. So when we do spectroscopy of the hydrogen vibration bonds on these different catalyst surfaces, including bulk palladium, palladium on gold, or palladium on ruthenium, we record the difference between wave numbers of the vibrational bond for hydrogen and deuterium on each of these catalysts. And we convert this separation factor in its expression in terms of this difference in wave numbers by adding just a speed of light constant here to basically express the frequency as the speed of light over the wavelength of the light, and the wave number is inverse of the wavelength. So basically this expression is relevant if we plug here delta W is differences between the wave numbers of the vibrational bond on different these surfaces or catalysts. So we do calculate the separation factors. It turns out that palladium monolayer on gold has the highest one, then palladium, monolayer on ruthenium, and palladium multilayer on ruthenium, which is bulk palladium, kind of very close, which means probably that compressive stress on ruthenium is not significantly affecting the activity of the palladium monolayer. What is really important in fundamental sense is that the ratios here between, if you normalize with the palladium bulk as the reference, then you can see that palladium monolayer on ruthenium underperforms, while palladium monolayer on gold uh, is better than by about 15% of the bulk palladium. If we do the same kind of a measurements using the mass spectroscopy, where we do electrolysis of the predetermined ratio of the water and heavy water, and we measure the ratio of the hydrogen deuterium in the gas phase, we get the similar separation factors. They're a little bit smaller, but the ratios that I talk about are fundamentally the same. And then we do the same type of the similar type of the measurements for the separation factors from the measurements of the kinetic parameters, such as the current for the pure deuterium sulfate dissolved in heavy water and regular water with the sulfuric acid for different catalysts, and we see pretty much that separation factors are again similar, but the ratio is about the same. And so in summary, you can see that these ratios that we are getting are fundamentally the same from different types of experiments where we measure separation factors, whether we use spectroscopy and calculations or mass spectroscopy experiment or kinetic data. We are getting about identical advantage of the palladium monolayers of gold as compared to bulk palladium or palladium monolayer ruthenium. Therefore, it's the theory and idea is proven to be correct. Now, the The question is how correct this is and how much relevance this have to industrial or scale-up process. So here I'll give you two examples. One is the basically Rayleigh equation, which tells you that if you start with this water, which has about 1.5 10 to the minus 4 fraction of hydrogen deuterium, and you want to enrich this water to be 99.7% heavy water, you use this equation, and basically, if you want to get 1 liter of ultra pure heavy water, how much in terms of the volume regular water you have to electrolyze, having a different separation factors for your catalyst. And you can see the bulk PD monolayers in the middle. They are better than hyper D metals. But the best of palladium monolayers on gold, where you have to electrolyze 25 cubic meter of water as compared to 40 for palladium bulk, or 70 to 500 cubic meters you compare this to hyper D metals used as a catalyst. In terms of the price, you know, if you just put some regular numbers for the price of electricity, you end up about having 1 liter of heavy water produced by palladium monolayer catalyst on gold to be about $6,000. Using bulk palladium is a order of $10,000, and using hyper D metals is all everywhere between 18 up to $100,000. If you use the cascade electrolysis and you do similar calculation and put the separation factors, you end up that if you use the palladium monolayer on gold versus bulk palladium, you can save about full layer of cascade. So you need 5 cascades for palladium monolayer on gold versus 6 for bulk palladium, which means you're saving about, or you're doubling the capacity twice. Or if you use hyper D metals, then the number of cascades about 13, 14, which is way more. So just in short to say, producing hydrogen by electrolytic means also producing heavy water, and the money that you can make is probably higher than just selling hydrogen. The second example that we work on is the materials that we try to develop as a barrier for hydrogen permeation in the existing infrastructure used for oil and gas. And the idea is that if we're going to be having hydrogen as a source produced from natural gas, and this hydrogen has to be transported using existing infrastructure of the and pipe network, which is already in place, we will have to coat these pipes with a permeation barrier to basically avoid the problems related to hydrogen embrittlement and fracture. And most of you are probably familiar with hydrogen embrittlement. If not, hydrogen embrittlement is one of the major problems concerning marine corrosion and corrosion of the military Navy vessels. It's a serious problem, especially in nuclear industry, because those are high temperature problems. But nevertheless, whenever we're talking about high strength steel used for typical pipe networks, this is even worse, because even at room temperature, hydrogen permeation results in a decarbonization of the steel and catastrophic failure of this. Therefore, to battle this thing, you can reduce the pressure, reducing the capacity of the pipelines. You can blend the hydrogen, which again have to be then separated through the membranes. But overall, if you can use the pure hydrogen under high pressure, your pipelines will be most efficient, and that requires some modifications. So when we survey the literature for hydrogen permeation materials, we see that copper is identified as the one that has about several orders of magnitude lower solubility and diffusivity of hydrogen than in a regular iron or steel. Therefore, we can actually pretty well calculate it from the well-known data, the effect of copper thin film barrier coatings on hydrogen permeation through a steel using the literature data. And this is what we have done here. So you can see that the hydrogen diffusivity in copper is of order at least 3 to 4 orders of magnitude lower than in steel, which is important. But also you can calculate permeation factors for, let's say, copper barrier layer here on 4340 steel at 300 Kelvin, which is room temperature. And you can see that if you put 1,000 times smaller thickness of the barrier than it's a wall of the steel, then you can reach the permeation reduction factors of about 100. In roughly, engineering language speaking, that means that you will probably reduce the potential of hydrogen embrittlement about 100 times. And therefore, if your steel pipes are designed to last 20 years and be not affected by corrosion, then most likely you will offset the hydrogen embrittlement problems to be about the same life cycle as initially designed for oil and gas. All right, so our research is basically having several stages. We are, first working in a laboratory on a beaker level where we develop coatings and test them and look in the structure, and then we evaluate a little bit larger coupons for permeation reduction factor using the one-ton cell. And then we model the transients from these experiments to also extract diffusivity, solubility, permeability of the hydrogen in this double layer membrane type of the structures. We also look into the grain analysis, grain boundaries to learn what really affects the best or reduces the best hydrogen diffusivity and permeation through this membrane. And then we go back, even improve further, and eventually look how to scale this up to a real pipe geometry. So here I give you an example why we go with the chemical deposition of copper permeation barriers. It's basically a very simple process where you have chemical reduction of copper ions in the solution with reducing agents. Could be, formic acid, could be something else. The bottom line is that you can achieve pretty fast and pretty high quality copper coatings on steel, which are relatively cheap as compared to any alternatives. And this could be scaled up fairly easy to any kind of a geometry, size. And it is, in general, a process that's been around for about 100 years, well understood. And what we really need to do is just fine tune the process to achieve the quality and um, I would say density of the copper coating that is appropriated for this application. So we have done a lot of work, especially this year, working and understanding the effects of different additives and reducing agents, complexing agents on the morphology of the copper coatings, crack formation or crack suppression, and I just give you, we have many more of this, but I just give you an idea what kind of a survey we have from effects of the concentration of the copper in the solution to effect of, complexing agents such as EDTA on the morphology of the copper coating. And we are really looking to the highest density coatings with no defects, no cracks, and these kind of things. Nevertheless, the final word about the quality of the barrier is done by real permeation test in, as I mentioned, the electrochemical permeation cell, where in the charging cell we produce hydrogen by hydrogen evolution reaction on the surface of our steel or double layer coupon, and this hydrogen evolution also causes hydrogen to permeate in the sample and exits the other side of the steel in the detection cell, where we measure the hydrogen oxidation current related to this hydrogen flux. And basically the ratio between these currents measured in a charging cell for the steel sample and steel sample coated with a permeation barrier layer of copper gives you permeation reduction factor. So thanks to Energy Transition Institute and Shell, we have received some funding. We developed the whole procedure and know-how in our lab for testing this using the permeation cell. And here's some data just to illustrate how good we are so far. So this is the steel coupon, which has about a micron or 300 nanometers copper layer electrolessly deposited. And these are the permeation transients for a steel sample, and this is the steel sample coated with 300 nanometer copper and with 700 nanometer copper. Steel sample thickness is about 700 microns. So you can see that permeation reduction factor increases to one order or two orders of magnitude depending on the thickness. And the thickness, when you consider 700 micron steel versus 700 nanometer, is really only tiny fraction of the steel wall. And therefore, when we look the calculations that we could do from the literature data, we can see that our permeation reduction factors are almost an order magnitude higher for the given ratio in the thickness between the steel and the copper permeation barrier. So we are doing pretty good in terms of decision what material to use and how to form these barriers. So then we can do more analysis of this um, permeation transients, and we can extract the diffusivity of the hydrogen through steel, through effective diffusivity to copper-coated steel. We can do some scientific evaluation. One of the things that I want to show you is that when we calculate the diffusivity of hydrogen in a copper that we electrodeposit or actually deposit on the steel versus the copper that is on the literature data, we are actually about 1,000 times smaller. So that means that our copper actually, besides being the right material, also is the copper that has a very special grain boundary composition with a lot of hydrogen traps, which retard the hydrogen permeation through it, and actually it even acts better than the regular copper. So we're doing very good. We right now, you know, patent application will be filed soon, but the proof of the concept is done. And since this is already funded by the Hydrogen uh, Institute and by the Department of Energy, we are comfortable to next year start some scale-up work to demonstrate the coating in a real pipe geometry and also test this in a Dr. Powell lab and eventually have uh, true demonstration of the idea. And the last thing I want to give you an idea what we do in terms of the sensing concept developed for hydrogen. We are combining several physical fundamental processes to develop a superb and super fast real-time sensing concept for hydrogen, which if you think about this, is essentially important for hydrogen becoming vector for energy, future energy conversion, since we know that the explosion threshold of hydrogen in air is only 4%. Therefore, any leak in a closed, confined space would be detrimental. It could be quite catastrophic. Not only that, hydrogen as a chemical is participating in many reactions. For example, ammonia production or some hydrogenation reaction. So therefore, pressure of hydrogen, accurate pressure of hydrogen, and reliable measurements are of great importance. Now, to give you an idea what really sensor we are trying to build is that basically it's a fiber optic, um, uh, and this fiber is having inscribed Bragg grading, and the concept behind this is that if you send the input light into this fiber with the Bragg grading, the only one that will be reflected without attenuation is the Bragg wavelength that is actually compliant to the Bragg grading periodicity. Therefore, that Bragg grading is giving us opportunity to monitor the shift in the wavelength of the Bragg light or Bragg wavelength. and monitor other processes that are imposed upon the fiber. Therefore, the shift is very sensitive to the strain in the grading. And if we coat the fiber with a particular material, for example, catalyst that is very active to hydrogen adsorption, then the Laplace pressure, because those are small diameter fibers, will be a function of the surface energy of the fiber coating, which is our catalyst material, and indirectly this surface energy will be modified by the adsorption process, which is going to be again function of the pressure of the hydrogen. And change in the pressure of the hydrogen will be reflected basically to the change in the or shift to the Bragg wavelength. And that's how you can actually measure tiny amounts of hydrogen or small pressure changes of hydrogen in the environment. So the physics behind this is a little bit of the thermodynamics. I'm not going to go too much into equations, but the bottom line is that you can see that surface energy of your catalyst coating of the fiber is a function of the pressure of the hydrogen, and the capillary pressure on the grating itself is a function of the surface energy of the coating, which is again function of the pressure of the hydrogen. Therefore, the strain in the grating is a function of the pressure of the hydrogen, and the shift of the Bragg wavelength is a function of the pressure of the hydrogen. That's the transducing mechanism that supposedly should be operating. Now, typically we can coat the Bragg uh, fiber Bragg fiber with gold, and we can put the palladium monolayer, which is super sensitive to hydrogen adsorption. We are well-known group who developed all these fancy methods to deposit and control monolayer deposition. Here, I just give you an example how sensitive palladium monolayer is on hydrogen adsorption. We can measure exactly a monolayer of hydrogen adsorbed on palladium monolayer on gold. Therefore, if I have gold-coated fiber and we put just palladium monolayer, that would be just about perfect sensor for hydrogen. And additionally, we can improve the sensitivity of, or actually selectivity of the sensor by introducing certain molecular frameworks in collaboration with the Professor Mark Little from Harvard University, where actually we can block the diffusion of any other gases than hydrogen by having a molecular framework with a particular porosity which can only let hydrogen molecules reach our palladium coated surface, but all other will be actually prevented. Therefore, we can actually have super selective sensor, not necessarily super sensitive one. And to give you an idea how this really well works, just to demonstrate this using data where we test the sensor performance, where instead of hydrogen we have a chloride ion in the solution going from 10 to the minus 6 molar concentration all the way to 10 to the minus 3. You can see the sensor performance and you can see the transducer equation model. And basically, the sensor is capable of detecting high concentration or low concentration, and it's really operational in different environments. In this particular case, we made the sensor also electrochemical, so we can actually change the potential on this fiber because this is in solution. But for the gas phase, it's going to be even simpler. And finally, the last conclusion is that this sensing concept that we are working on is generally applicable to adsorption situation, which could be gas, organic, ion adsorption, anything. And it should be actually improved very much more because we can use fiber with a smaller radius, which would give immediately higher signal to noise ratio. We use differential sensing concept, which also reduces the noise in the data, and with the advancement in the coding engineering and this selective layers that we are working with Dr. Mark, we're pretty sure we're going to have a superb hydrogen gas sensor probably very soon. Thank you for your attention. It was great pleasure to present my work today. Thank you.
Thank you very much, Stanko. If there are any questions, you can unmute yourself and ask. We have a question in the chat from John Karanikas, and he asks, John, do you want to ask the question or?
Okay, I can ask the question.
Yeah.
Thanks for the presentations. The question is on the copper layer on the pipelines. So
Yes.
the pipelines are going to be exposed in the ambient. Of course, I can imagine coming from anywhere to anywhere from freezing temperatures to 100 degrees Fahrenheit. Question is if there is a differential thermal expansion between the steel and the copper, how robust would our copper layer be uh, to the hydrogen? Would it allow some places for hydrogen to go through and attack the steel? That's the question. As the temperatures expand as the material expand differentially.
Yes. So the thermal expansion coefficient of copper and steel are very close. They
Yeah.
virtually do not differ. That's one of the choices why the copper is good. Second, the copper we make is actually, I mean, the copper has a high yield, plasticity, and so on. So it's not really a brittle material. It's actually very, you know, it can withstand large plastic deformations. Therefore, um, in that sense, for the room temperature application, which we consider pipe networks, which means, freezing or below freezing up to, let's say, 120 Fahrenheit. Um, for this type of the temperature variations with such a small difference in the thermal coefficients, we are way we are really safe. Now, if that would require, going to like a nuclear reactor type of the environment where we're talking about, 800 degrees, then maybe we would have a problem because those small coefficient difference could actually multiply by 800 degrees, could be a problem. But for the room temperature or ambient temperature application, this is not an issue. In fact, our copper, the way that we are synthesizing is actually very, it's actually better than the pure copper because, through synthesis process, we introduce certain impurities which actually act as a hydrogen traps, which additionally slow down permeation process, but also they increase ductility of the copper and they improve the grain boundary quality of the copper. Therefore, unlike in a pure copper where the grain boundaries represent a fast diffusion path for hydrogen, in our case, our grain boundaries are saturated with those hydrogen traps, and actually, hydrogen does not permeate through the grain boundaries of copper, which is kind of interesting, thing. And thus, we are confident. I mean, at least I'm sure that this is the right thing to do. Of course, to do the right thing, we need to study this a little bit more and test more, and the scale up should be done carefully from you know laboratory up to you know first level, which is still demonstrational, up to the level where you can go and do the first pipe line coatings and so on. But I'm pretty sure, comparing to what is available as alternatives, where the synthesis methods of different barriers, like epoxies, whatever, require high temperatures, all these things, we can go underline pipe, and coat it with a really extremely competitive price as compared to existing situation. Now, if the company decides to put some inserts or liners, pipe within a pipe type thing, that's extremely expensive. Then, I don't even need to convince anybody that this is the way to go. But for the new pipes, we also have advantage because if you already have pipe out of the ground and you just, preparing it for installation, then the coating is even way easier. But we had in mind developing this idea is what would be the easiest way to coat the pipe, and so the pig that is already used for cleaning the pipe, surveying the pipe, is actually very compatible with the idea of having a chemical coating of the pipes, because you can move the pig with a solution. Of course, this has to be still tested. I haven't done all this stuff, but it's compatible with existing hardware, with the small alterations or augmentations of the hardware. Probably the process itself will work with what is already available in the oil and gas industry. So I'm confident, and with more money, we can do certainly more for sure.
Great. There's another question from Barbara. Barbara, if you want to unmute yourself and ask.
I noticed you're using the gold as a substrate, and of course, that's not right now an industrial metal. It's pretty much controlled by the financial markets.
Mhm.
And so my question was, what kind of a ratio of gold to as the underlying straight versus that small layer of palladium do you need?
Yeah, so I didn't say too much about this. Why gold? Okay, let me give you an idea. So we are not going to use gold as a bulk gold. So the gold itself, as a substrate, will be actually also a few monolayers only on something which is cheap. Let's say some kind of a nickel, steel, whatever, right? We need gold just because the gold lattice is bigger than palladium, and if you put palladium and epitaxial relation is preserved, palladium will be stretched and super reactive and better than the regular palladium. So in that respect, we know how to do well palladium monolayers, platinum monolayers, all this stuff. And gold, few monolayers on something else, is not like industrial use of gold, which is going to kick the price so up. Because for industrial electrolyzers, one of the reasons why people are now looking into precious metals again is that progress in this monolayer catalyst design. If you use platinum, palladium, or these precious metals, the over potential you need for electrolysis to get the same current that you get on the hyper D metals or nickel, whatever, is about 10 times smaller. That means 10 times less power you're using. And when it comes to the power, that's electricity cost. So operational cost of the electrolyzers with the precious metals, with the monolayer concept, installation is not expensive as initially you might think, because we are not using a bulk type of the things. We're using very modest amounts, which again could be calculated. I can give you an idea. At the same time, on a long-term operational cost is way lower than any other electrolyzers, because we don't need a high over potential, so we don't need the power and in terms of electricity that is spent per same kind of a currents that we will generate. And current is basically hydrogen flux. And very important thing is this is not this is neglected as a concept to produce hydrogen isotopes whenever you have electrolysis. The hydrogen itself is news product. The way more expensive product is the heavy water. Now, obviously, if you need a hydrogen, you will have to produce it, but at the same time, you will be enriching you will be producing even more valuable commodity, which is the isotopes. For example, tritium. I think tritium is right now the short stopper for the fusion expansion if it's working, because tritium is actually quite expensive. And the way it's produced is the bombardment of the lithium targets with neutrons. It's called the lithium breeding. So it's super expensive. You need to have a reactor surrounded with the lithium-6. It's complicated. Military has money for the stockpile. That's not even a point. But there's a lot of tritium in every nuclear reactor, which is used, whether it's a moderator, the regular water or heavy water. There's a lot of tritium there. And if you electrolyze this water, you will have plenty of tritium to run fusion reactor.
I think that, yeah, that byproduct
Yes,
turns out to be
tritium,
better than the actual volume product, which is a
exactly.
wonderful thought.
Exactly. This is why I'm telling you this. So it's not about hydrogen here. You will produce hydrogen, that's okay. But why not we improve a little bit or tune the process so we can produce a lot more efficiently hydrogen and at the same time hydrogen separate hydrogen isotope. And
So if you were doing this across the state of Texas, um, how much precious metals would you need? Would you need ounces, pounds, tons to, if
the,
you did it on a scale? Just out of curiosity, I haven't a clue.
I would say I'm not sure what would be the capacity we're talking about, but let's say if we want to switch to hydrogen economy now, we only produce hydrogen from electricity, and you know, instead of battery, we produce hydrogen, then we use hydrogen for a fuel cell cars. Let's say this is more efficient concept than using electricity for battery cars. And so if we're going to do that, and currently, how many battery cars we replace with the fuel cell cars, and we need a clean hydrogen, which means we need to electrolyze water. Probably for the whole state, I would say no more than, um, in terms of palladium, certainly no more than, a couple 100 ounces, and in terms of gold, probably a few times more. But we're talking about relatively modest amount. Keep in mind, this is a monolayer. It's atomic monolayer that works so well.
That
So,
was my guess, and I just wanted you to confirm that it's the
so let's
small
say,
number,
we are
not the
talking
larger.
about a cost that is not going to change the demand or price of the precious metals on the London stock exchange.
Well,
It's
and more importantly, it won't cut into the rest of the economy for that metal by
no, no,
the way copper is having a problem now
no, no.
uh, with the all sorts of the green energy
Yes,
taking more copper than anything else.
no, no. Because I can give you an idea. Uh, Basically, if you want to cover 1 centimeter uh, area with a monolayer of uh, palladium, you need about 10 to the minus 7 moles, and mole of palladium is around. So basically, we're talking about something in the micrograms amount. So centimeter is a microgram, square meter is a 10 to the minus 2 grams. So 100 meters is about a gram of palladium, roughly. Let's say a few grams of palladium, 100 meters. All
So
right.
this is very practical as far as the amount of
Yes,
material.
yes, yeah. This is the whole idea. Yeah. Otherwise, it would be, cool idea, but practically limited. But this is not practically limited. That's the point.
So how for copper linings, is that similar, the amount that's needed for 100 miles of piping,
Yeah,
because it's so thin, still
yeah, yeah.
isn't going
I
to,
calculated the price per mile
ooh,
in one of the proposals if we apply these barrier layers made of copper, and I used the 8-inch steel pipe. I think the price was in about less than 10 cents per kilometer, I think, or something. Something. I need to look this. I don't want to give you wrong information. I would need to look into this proposal, but I did calculations. It's actually very, very cheap because the chemicals that are we using are not high purity ones, and then those are, copper salt is cheaper than copper. Keep in mind that, it's not like you're buying metallic copper. You're buying a copper sulfate, which is about 5 times cheaper than copper. And so, and then application-wise doesn't require reactor vessels, all this stuff. This is, you saw it's a solution-based concept. So it's super cheap. Application-wise, it's really not. It's actually very competitive with anything you can think of today proposed as a hydrogen barrier coatings.
well,
Then you
and it's
get
very clever in that it does not significantly impact the copper market for other uses,
no, no,
which is
no.
often a problem with these proposals.
No, 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 no. I mean, I have done this calculation for this proposal. Unfortunately, I don't want to give you data that are wrong. I would I can send you an email and give you an idea. You just shoot me an email with a question.